Hello, this is going to be 9A. This is going to talk about waves and water dynamics. And as you can see, we have a picture of the Earth here, and this is wave height. And we got red for the high. This is 6 meters. You can see some really dark reds in there. And you can see greens and blues. And then all the way over to, actually I don't see any of this color. But basically the blues, very little wind. Greens, a little more wind. And reds a whole lot, yellows and reds a whole lot of wind, because that's the driving force. And I've shown you this site before. Let's go to Earth Null, and if we click Earth, we can go down to Ocean, and we can hit Waves. And this is a picture of the Earth's waves, and they tend to actually be really heavy. Let's actually look at this Antarctic view. They tend to be really heavy down here, not so much because the wind is strong, but it is, but because it's always almost coming from the same direction. So most of the really high waves, and especially this section of South America, it's like putting your thumb over a hose, and as the water goes through, it goes through a lot faster. So we actually do get surface currents up here, but we also get the winds. Okay, it's always important to heed waves. I'm pretty sure this was planned, because I'm not sure this probably was not the first wave to come through, but you can see this couple smiling, and here comes the wave. She looks a little more animated here, maybe because the water's cold, but you can see it eventually wipes them out. So energy in waves is actually pretty high. If you've ever been to an ocean or felt these waves, they are pretty amazing. Waves are moving energy. The force for this is actually usually air, and this air moves across the surface of the water, and it transfers some of its energy into the water molecules, and they get drug along, if that's a word, dragged. They get drug along. Wind is usually the cause of surface waves. Movement of fluids in different densities also do the same sort of thing. So we actually do have these internal waves, which we talked about before. These tend to be a lot larger. They tend to move a little slower because it's moving through a more viscous, a thicker material than the stuff up here moving through the air. It can also be caused by mass movement in the ocean, like landslides. And if you take a look at this picture where you see relatively smooth ocean, that water molecule is not really moving, at least doesn't have a gross motion. It does have a motion, but it ends up being right back where it's supposed to. But if you see these white caps, these are actually water molecules that are moving forward, and they're not coming back. Seafloor movement, we have things called tsunamis, or what are called harbor waves. They're also called seismic sea waves, probably a better way than saying tidal wave, because it has nothing to do with tides. This picture, when it pops up, this is something that I want you to draw. And excuse me, and this is what I would like you guys to draw. And what we have going on here is the displacement. If you look at the arrows, this has to be a convergence zone. So there was an earthquake, we had land move, and that land energy moves into the water and starts causing an upward movement of water. You're probably not going to see this thing out in open ocean, but when it gets into shallow water, it turns into a shallow water wave, and we'll talk about that. Stands up and has all the things that you've seen in terms of real tidal waves or ones in movies. Gravitational attraction of the Earth, Moon, and Sun will cause waves too. These are the tides. Remember, tides are always going to be shallow water waves, and that's because their wavelength is so far that we can't have an ocean deep enough to let them ride. Human activities can do this as well. Here's a picture of a boat. You can see normal wave patterns going on, and then you can see the interference caused by the wake of this ship. And we can also have explosions in water, and it's used for a whole lot of reasons. Usually we're throwing explosives into the water so that the explosion bounces off the bottom and tells us where oil is located down inside the sediments. Earth Null School again. These are waves. They actually start off with very, very small waves. If you take a look at, this one doesn't actually say height, but it does talk about how long it takes to get from one wave to another. So our wave period is 1/10 of a second, so they're going like 10 per second. They get a little bigger, they slow down a little bit in terms of frequency. In other words, they spread out. They're 1 second apart. I wish it really had thought it had height on here too. But basically what happens as they get bigger and bigger, and these are what are called gravity waves. Gravity waves are things that are actually fighting gravity. If the waves get too small, eventually the waves will get pulled back down by gravity down to the surface. But wind causes these waves. These are actually caused by wind and ordinary stuff. These are infra-gravity waves, which means they're actually starting to pass through these differences. If we get really strong wind, like hurricanes or really strong winds, big thunderstorms, we can get waves. Earthquakes can cause waves, and then we have ordinary tidal waves, and we have what are called trans-tidal waves, and these are actually waves that are caused by storms and sun and wind. So we have basically all these waves going through. These are very small, very quick, very close together, and then they can get bigger and bigger, and eventually gravity will start pulling those back down, and then we start getting faster and faster waves that are farther and farther apart. So they're actually caused by wind, and remember in the northern hemisphere our storms go counterclockwise. This is the area of generation. Generation, that's correct. Combined long and intermediate period waves. In other words, there are a whole bunch of different sizes, and then as they get away from the storm they start separating. The long periods actually move faster, so they separate from the shorter intermediate period waves, and smaller period waves would actually still be there and probably pulled back down because of gravity. So this actually started the water to move, and gravity is going to be the settling force. Progression of waves, we have what's called longitudinal. This is a push-pull. The water's moving this way. We have, and actually there it is, so we have the water actually moving this direction, then it will actually move back this way, and then it'll move this way, and it'll move this way, and I'll show you an animation. We also have what's called transverse motion. This is the up and down, where the molecule would go up, and then it would come back down, and then it would go up, and then come back down, and it actually takes this circular pattern. And then we have what is called orbital, and this is the circular motion, which is actually the side to side and up and down, which gives it this motion. Okay, so you actually, as this wave moves this direction, you can see this thing would go up in the crest, and then it would slide back down and backward in the trough, and then up and forward in the crest, and back down. This is not the animation. And this is how ocean surface waves go. As long as the water molecules aren't falling over, in other words, it's not a breaker or a white cap, the water molecules end up right back where they started. Here's a depiction of it. This is one of just particle physics, and if you take a look at the yellow blob right there, as that trough comes in, it goes forward and up, and as the crest passes, it goes down and back into the trough. And they all work this way. At the surface they go faster, and as they go down they slow down, and eventually they'll stop moving, although these guys are still moving. So here's two animations. Here's a gull moving up and down, but you notice the gull stops right back where he or she started. So as the wave goes, they go forward and down and backward and up. And here's a bottle or a buoy sitting in the same situation, waves progressing in the different direction, so it's actually moving backward, and here comes up and forward, and then backward and down and up and forward. And this is the motion that can make people sick, because the stomach is trying to go up and down, it's trying to go side to side, but it's going in a circular motion. So remember, we have longitudinal wave, which are moving side to side, a transverse wave moving up and down, and then we have what's called the orbital wave, which is actually what the particles in the wave actually do. There's another draw thing, so I'd like you to draw that picture. Wave characteristics, crest and a trough. Crest is the high point, trough is the low point. We have what's called wave height, which is the difference between the crest and the trough. Usually it's given in inches or feet. If we're actually talking about electromagnetic waves, it's like gamma waves and visible light waves, it's a lot smaller, but can also be a lot larger. If we talk about infrared, infrared can actually be larger than the Earth, so we could put the Earth inside of one of these. We also have what's called wavelength. This is a crest to a crest, or a trough to a trough, or that midline right there to that midline right there, or that one to that one, or this point to that point. It's one part of one wave to the same part of the next consecutive wave. Then we have what is called wave height and wavelength, where we actually take the height, then we divide it by the length, and this gives us what's called steepness, and this is what's going to determine whether the water breaks. And this happens when the wave gets closer to shore, and you can see there's another draw thing, closer to shore, and the bottom actually is sort of slowed down because it's hitting soil or sand, and the top it falls over because the wave gets too steep. Waves break when the height length is equal to 1 to 7. So the height 1 and the distance 7. Anytime it gets more steep than this, which is like 1 to 6, 1 to 5, and it basically means the waves are getting closer together, and they may even be standing up, the wave will break. Wave period or frequency, this is the time needed for one complete cycle. There's a cycle to pass one point. So you watch one crest come in, you look at the next crest that comes in, actually this crest to that crest because it says it's moving this way in time. So you count this crest and then you count the number of seconds to this crest, and this would be the period. Frequency would be the number of waves you actually see per minute or per hour or per second or whatever unit, but period is actually talking about how much time is there between waves. Wave characteristics, wave base is equal to 1/2 of the length. So if you have this length, and let's say this is 10 feet, the base of the wave goes down half of that, which is 5. So you're going to feel this orbital motion less and less and less until you actually get to the base, and below that you actually don't really have anything, and it's 1/2 the wavelength. So take the length of the wave, divide it by 2, and that's how deep. Like if you had a really big wave coming, what you can do is you could actually calculate how far these waves are, and that would tell you how far you have to dive down to get either to slower water, so you're not, ripped apart up here, or down to a place where there is no depth. Deep water waves, these are waves when the water is greater than 1/2 the wavelength. In other words, the wave does not touch the bottom. This is the depth is equal to bigger than the length divided by 2. If you take a look at this, these are shallow water waves, intermediate, these are deep, and the deep is L, DL is greater than 1/2. And then you can see we have DL is less than 1, that's 5/100, so 1/20th. And then intermediate waves are much more complicated. These are relatively easy to calculate, but this one, because we're throwing in all these variables, can be a lot more difficult to do. Speed of this wave, or what's called silicity, is proportional to the wavelength. So if you actually take a look at the wavelength, as the wave gets closer together, they get faster and faster and faster. Shallow water waves, this is anytime the water gets less than 1/20th of the wavelength. And this means the wave is actually touching the bottom. It actually flattens out these ovals. It actually slows down the bottom. It's like you're running through a race and somebody trips you, or at least slows your feet down. And then what it does, it actually makes the wave eventually fall over. So this is D is equal to L divided by, or less than L divided by 20. Friction of the seafloor retards the speed. Wave speed or silicity, celerity is proportional to the depth of the water. And orbital motion does flatten out. Transitional waves, these are somewhere between deep water waves and shallow water waves, and they're a lot more complicated. Characteristics of deep, if it's closer to this one, shallow if it's closer to this one, and the wave speed or celerity is actually proportional to both the wavelength and the depth of the water. So 3 types of waves, and this should be the end. What I'd like you to do is actually to write down the definitions for these, and primarily the bottom one, but the way you deduce that is the top one. I'd like you to do that. It does tell you greater and less than, and you're going to have to pause that because I'm not going to talk about these two again. Wave speed, wavelength divided by period. Its celerity is equal to length divided by time. Frequency is 1 divided by the period of the wave, so frequency is 1 divided by t. And then wave speed, meters per second, 1.56 times the period. So you take the speed of the wave is equal to 1.56 times the time. And typically 8-second trade wind waves move at about 28 miles an hour. That's 12.4 meters per second, but 28 miles an hour, so like 30 miles an hour. And there's the stop. Thank you much for stopping by. And that's the end of 9A, Oceanography.